Go ahead. Thanks.
Okay, can you remove? Okay. Yeah, so for the past decade or so, we thought that pulsars could produce sharp spectral features in the local cosmic ray electron and positron spectra, and I'm going to show you now that this is not the case. So this is the local cosmic ray positron flux as measured by the AMSO2 experiment that currently gives us the most precise cosmic ray data. And there are two things about this positron flux that are noticeable. The first one is that at above about 20 GeV, we have this rise in the positron flux that was unexpected when it was first measured and is now called the positron excess. And then the other thing is that this flux is actually very smooth, and this is important so we can keep it in mind for later. And so there are different components to the positron flux. So at low energies, we have a pointer, yeah, there. We have the contribution from secondary positrons, and these are just positrons that are produced in interactions of other particles with the interstellar medium. And then at higher energies, where we have this positron excess, now the most prominent explanation is that these positrons are produced by pulsars that rotate very rapidly and convert some of this rotational energy into electron-positron pairs. So we get also an equal contribution in the electron flux, but because there are so many electron sources, the pulsar contribution is quite insignificant. So I'm going to focus here on just the positrons. And then potentially we have a third contribution from dark matter particles that annihilate and would produce this very sharp and spiky feature at the dark matter mass. Now, we don't know exactly how many pulsars contribute to the positron flux, but we can still make models of the spectrum of an individual pulsar and its contribution to the positron flux. And throughout this talk, I'm going to use the pulsar Geminga as an example because it's probably the pulsar that contributes most strongly to the positron flux. And it's middle-aged, so it's 370,000 years old, and it's quite nearby. It's just 250 parsecs away. And in this plot here, you can see a model, an analytic model of the contribution from Geminga. And what we can see here is that we get this sharp feature and then also this very sudden cutoff. And in fact, this feature is actually very common for many papers that model the contribution of an individual pulsar. So as you can see in these plots, many of these show these sharp features. It also depends a bit, of course, on the exact parameters that you choose, but this is a very common feature, and it's also very puzzling, right? Because we said that the positron flux is very smooth, so we don't necessarily expect there to be any major sources that would introduce such a sharp feature. And also, we said that annihilating dark matter would produce such a sharp spectral feature. So we really want to understand the pulsar sharp spectral feature so that we can distinguish it from dark matter should we ever see such a sharp feature. So now I'm going to explain to you why we would expect a sharp spectral feature from pulsar models, and then I'm going to explain to you why we don't. So what happens is that a very large fraction of the total positrons that a pulsar produces over its entire lifetime is produced in the first 1,000 of years when the pulsar is very young. So we get a lot of positrons at once, and even though these are all produced at different energies, there's also the fact that high energy positrons cool faster than low energy positrons. And they lose energy in magnetic fields and the interstellar radiation field as they propagate. So we can see in this plot here, I can't really point, the energy of the positron as a function of time. And we see, for example, if we look at the red line, which is for a positron that has an initial energy of 1000 TeV, this particle loses most of its energy in just the first 100,000 years. And compared to that, the blue line is a positron that starts at 1 TeV, only loses a much smaller fraction of its energy in the same amount of time. So we have a lot of positrons produced at different energies, but they all cool down to the same energy given enough time. You can also see this in this plot here, where we have the spectrum of a pulsar at different ages, and we see how this feature moves to lower energies over time because the positrons have had time to cool. And then also this feature becomes more stronger because more positrons have time to cool down to that energy. So this is how we get this feature. And as you can see, this actually doesn't come from the pulsar directly, but it's something that happens when the positrons propagate and cool. So to understand this feature and where it comes from better, we need to look at what happens when positrons cool and propagate. So there are two cooling mechanisms that are relevant here. One is synchronization, so positrons are charged particles, so they interact in the magnetic fields in a galaxy and lose energy through synchronization. And then the other one is inverse Compton scattering, where a high energy positron interacts with one of the photons of the interstellar radiation field. So this can, for example, be a CMB photon or a starlight photon, and gives off some of this energy to the photon and loses energy itself. And the energy loss rate is given by this equation here. And we have a term for, this point is very strange, for synchrotron and one for inverse Compton scattering. Now the details of this equation are not really important right now, but what's important to notice about this is that this equation treats energy losses as a continuous process. And this is fine for synchronization because it's essentially a continuous process. But for inverse Compton scattering, this is actually different because this is a very probabilistic process. There's just a small probability that an inverse Compton scattering interaction happens in a certain period of time. And the energy losses can be quite catastrophic as well. So if you take this into account, this stochasticity of inverse Compton scattering, then you actually realize that the energy losses from inverse Compton scattering are very individual for each positron. So we created a model to take this into account, and it works like this. We create a positron at some initial energy, and then we involve this in time. So we, of course, take into account the energy losses from synchronization, and then in each time step, we use a Monte Carlo to determine if an inverse Compton scattering interaction happens and at what photon energy. And then we calculate the energy losses from there and the new positron energy, and then we keep doing this until we have reached the age of the pulsar, because that's the amount of time that these particles have at time to cool. And then this is our result. So I want to point out that in the continuous approximation, the analytic calculation, all positrons are treated in exactly the same way, and they experience exactly the same cooling. So they will end up all at the same final energy. Now if we treat inverse Compton scattering stochastically, this is not the case anymore. So in this plot here, we have the final electron or positron energy, it doesn't matter, and the average energy loss per inverse Compton scattering interaction. And all of these positrons started at 10 TeV and cooled for 370,000 years. And we see here that we get a spread in energies, or in both of these parameters, that's about 30%. Also, it turns out that inverse Compton scattering interactions are quite rare. For 370,000 years, we had on average about 120 interactions per positron. Some of these energy losses can also be, they vary a lot in strength, and they can be very catastrophic. As you can see in this plot, we have the energy as a function of time, and the dashed line is the calculation from the analytic approximation, and then the solid line is the average of our stochastic model, and the gray shaded regions are the 1 and 2 sigma bands from our stochastic model. And then the colored lines are just a few examples of individual positrons as they cooled. And we can see then this orange one just had some massive energy loss there. So yeah, you can see that this is very stochastic. And in the end, we have a spread of final energies of about 30% compared to the single value we got from the analytic model. So if we now go back to our pulsar model and take the stochastic inverse Compton scattering into account, we get this result. So in blue, we have, again, the analytic model with the sharp feature. And now compared to that, we have the orange line, which is our result, where we took the stochasticity into account. And we can see that the top of this peak is very round compared to the analytic model. And also this sharp cutoff gets smeared out so that we get a spread of around 50% of this feature. So we see that pulsars cannot produce sharp spectral features. And this is actually also interesting if we come back to the question of how many pulsars contribute to the positron flux. Because if you want to fit many pulsars to this very smooth positron flux, you generally end up with a large amount of pulsars so that you can wash out these sharp features. And now that we see that pulsars don't produce sharp features, this actually opens up the possibility again that maybe only a few pulsars contribute to the positron flux. But we can't really make a statement on that because it could be a lot, it could be a few. So we don't know how many it is. So really what this result does is actually that it loosens the constraints on pulsars. And finally, if we come back to dark matter, so the situation for dark matter is different because we said for pulsars, this feature comes later when the positrons cool, but for dark matter, this feature or this sharp signal is introduced when the dark matter annihilates. So the origin of this sharp feature is quite different. And this is why dark matter will not be affected by this. So we still get sharp features from dark matter. And it also means that now dark matter is actually the only known potential source of sharp signals in the positron flux. Then finally, I just have my summary. It's very short. And it's just I showed you here that if we treat inverse content scattering stochastically, we can see that in our pulsar models, we will not expect any sharp features.